Hello, and welcome back to my factoring series. Today, we're going to be working on factoring binomial terms, which I will get to what a binomial is shortly. But I want to start by going over distribution first, since it's kind of going to be the basis of our understanding. So let's assume we have a situation like this, where we have some quantity in parentheses. So in this case, it's a difference. It's x minus 1. And then I have multiplying to this entire parentheses the number 3. So hopefully we're all at the point where we understand what to do with this. If not, and you're seeing this for the first time, I'll go over it slowly. This 3 on the outside, even though we don't have a little multiplication symbol here, we assume that this 3 is multiplying rather than dividing or adding or subtracting. And when we have a situation like this, we are supposed to take that 3 and multiply it to both parts of that internal parentheses. So this would end up giving us 3x minus 3. Now let's look at that with just plain numbers. So let's say we have 3 plus 1, so this time it's a sum. And I want to multiply this by the number 4. Now, typically using order of operations, PEMDAS, I know I should do what's inside of the parentheses first, right? So I should add 3 and 4 to, or I'm sorry, 3 and 1 together to create 4. And then I can multiply by the 4 on the outside, which gives me 16. But what if we instead decided to multiply, to distribute that 4 inside of the parentheses first? All right, so I have 4 times 3, which is 12. And I have 4 times 1, which is 4, which also gives me 16. What does G-force want right now? Okay, so you can see that even though I didn't follow the normal order of operations, this still got me to the same answer. It still got me to the right answer. So I want you to keep in mind that this is kind of how I'm showing you that this distribution is a valid thing to do. I know that if I distribute numbers inside parentheses, I get the answer I was expecting. So hopefully that's enough to convince you that it is an appropriate way to handle business in algebra. Let's go ahead and let's just look at a number, 45. And I'm going to go ahead and split up 45 into 30 plus 15. And next, what I want to do is I want to consider what the greatest common factor between these two things is. So I am going to look at 30. I'm going to look at 15. 15 is fairly easy. It's just 3 times 5. So those are just 2 prime numbers, and we can't go any further than that. For 30, I have 2 times 15, and 15, as we just saw, was 3 times 5. So it looks like the greatest common factor between 30 and 15 is 15. So here's what I'm going to choose to do. I'm going to choose to rewrite 30 as 2 times 15. And I'm going to choose to rewrite 15 as 1 times 15. And then what I'm going to do is I'm going to say, I want to take the common factor out of each of these terms, which is 15, and I'm going to put it out in front. And then I'm going to leave what is left behind in parentheses. So this way I have something that if I were to distribute back out, so 15 times 2 is 30, 15 times 1 is 15. Notice that I get the same thing that I had before. So this is our method here, how we're going to factor a binomial, which binomial just means we have 2 terms that are separated by a sum or a difference. So it's like blah plus blah or blah minus blah. That's a binomial. So that's kind of how we're going to do things. We're going to look at our two terms and we're going to say, hey, what's the biggest thing the two of them have in common? And we're just going to factor that out. And so this is why I wanted to introduce distribution first, because what we're doing is basically backwards distribution. We're going the opposite way. So let's just go ahead. Let's get an easy one. Let's say 2x plus 4. Now, I don't think I need to go through the factor trees. I think we can pretty plainly see that the biggest thing that 2x and 4 have in common is just the number 2. So I'm going to go ahead and, for all of our sakes, for, thoroughness, because we're doing this kind of for the first time here, is to rewrite this as that term, or excuse me, the sort of factor form where I have the greatest common factor times whatever's left. So 2x becomes 2 times x, 4 becomes 2 times 2, and I can clearly see that both of them have a 2 in them that I can then factor out. So I have 2 and then x plus 2. So that's a fairly simple one there. Let's get a little more difficult. I'm not going to go too crazy, but let's say I have, say 3x squared plus 36x. Okay, so this one is a little more in depth. I'll go ahead and, just because, let's go ahead and split them up using prime factors. So remember, when I have a term that is both numbers and variables, I kind of like to split the factor, or excuse me, the term into one and then the other. So I say numbers over there, variables over there. It's a little easier to work with if I do that. So 3 is already a prime number, so I don't have to go any further with 3. X squared becomes x times x. So 3x squared is pretty simple. It's just 3 times x. Not a whole lot happening there. 36x will be a little more complex. So I have 36 on one side, and I've got x on the other side. 36, there's a bunch of ways we could choose to split this up. I'm going to choose to split this up as 3 times 12. 3 is prime, so there's not much for me to go and do after that. 12 is 3 times 4, and 4 is 2 times 2. So there is a lot of factors in 36x, but let's try and see what's in common between 3x squared and 36x. So 3x squared, I see a 3 and an x. And in 36x, I see a 3 and an x. Now, obviously, they have other terms that, or excuse me, other factors that are not shared between them, which will be kind of what is left over. So for example, 3x squared, I'm going to separate it into 3x times x. So it's the greatest common factor that we found times whatever is left behind. So for 36x, I have 3x as the greatest common factor, and then all this other stuff is left behind. So 3 times 2 times 2. So 3 times 2 is 6, times 2 again is 12. So the stuff left behind is 12. And I can go ahead and grab just the 3x as the common term between the two of them, and I can rewrite it like that. And that's the factored form of this binomial. I do want to show you, fairly short lesson today, but I do want to show you that we can expand on this for bigger expressions. So if it's not just a binomial, in other words, if it's not just 2 terms, if it's 3 terms, if it's 4 terms, if it's however many terms, we can still kind of utilize this method so long as every term has a common factor between them. So for example, if I said 6x cubed plus 9x squared plus, say, 15x, I can look at this and I can say, okay, what do all 3 of these have in common? I can tell that these numbers all have a factor of 3 in them. And I can look at them and say that, well, all of them have at least one x, right? So I can go ahead and break this down if I would like to. If I would like to do it the long way. So 6x cubed is 6 times x cubed. Just to shorthand it, I'll say x cubed is just x times x times x. Usually I do it in more steps, but I think we understand what's going on. 6 becomes 3 times 2. Cool, great. How about, I'll do it in a different color, 9x squared. Well, that's x squared times 9. X squared is x times x. 9 is 3 times 3. Cool. How about 15x? 15x is 15 times x. 15 we did a little bit earlier. We know that's 3 times 5. Okay, cool. Great. So what do we see in common? I see 3 and x in all of these. 3x. Okay. And so I just need to rewrite each individual part of this expression as 3x times whatever they've got left. So 3x times, so for 6x cubed, it would be 3x times 2x squared. For 9x squared, it is, looks like 3x times 3x. Interesting. Oh man, I'm running out of room. I'm going to have to get rid of this guy for a little bit. And for 15x, it is 3x times 5. All right then. And then the last thing is to just pull out the common term and put everything else into a pair of parentheses. 3x plus 5. Awesome. So once again, demonstrated, even though the goal here was to teach you how to just factor simple binomial terms, you can also take this common factor type of situation and apply it to bigger and bigger expressions. So as long as all of your terms, all of your individual terms in your expression have the same common factor, you can factor out using this method. Now I want to do a little bit, like one extra thing. So let's see, how about 10x squared y plus, say, 15y squared. Just to show that you can do this with more than one variable included. So I'll go ahead and do the factor trees. Man, I hope you guys can't pick up what's going on outside. It is loud out there. Okay, so I got 10x squared y. I'll just do this one completely first, and then I'll head on over to the 15y squared. Okay, so 10 is 2 times 5, and then x squared y is x squared and y, and then x squared is x and x. Okay, so that is my prime factorization of that one. And then I have 15 and y squared here. I have y squared is y times y, which my handwriting isn't the best. I hope you guys can tell that those are y's. And then 15 is just 3 times 5. So let's look at each of these to figure out what's in common. They each have a 5 in them. Cool. They each have one y in them. And everything else seems to be extra. So for 10x squared y, we have, looks like 5 times y, or 5y times 2x squared. And then on the other side here, 15y squared is 5y times 3y. And then once again, we see what's in common between the two of them. That comes out. So 5y times, or why is there an equal sign? Times the quantity 2x plus 3y. So this is kind of, this is a big deal. I know it seems well, hopefully for a lot of you, it seems fairly easy. And if it doesn't seem easy, it just takes some practice. But this is going to be sort of your first step in general factoring. You always want to approach when you've been given a factoring problem. The first thing you want to do is you want to look at it and you want to say, is there something in common with all of these terms? Is there something I can just pull straight out of all of them? And it's always the first step you should take. So that's all I have for you today. I hope that you guys have grasped sort of what I'm trying to tell you here. Good luck with the practice problems, and I'll see you in the next video.